Just give a little woo and take a small sip, please. Please. There we go.
I will say it a lot. Okay. Yeah, thanks, Michael. So, yeah, I'm going to talk a little bit about LRO exploration. So this includes looking for potential resources like water ice at the poles, and then also to look for landing sites. You know, we have the upcoming Artemis missions. We have all of these current and upcoming commercial lander and rover missions. So LRO does a lot of work to help prepare to pick out where and why they're going to land at specific locations on the moon. All right, so one of the really cool things about LRO is it doesn't just look at the moon in the visible, so it actually looks at a wide range of wavelengths. Yeah. So it has a whole bunch of different instruments on it that have capabilities to look in the infrared or the ultraviolet or at the radar, as well as several other instruments. And we essentially use those to do a lot of really cool science. I'm going to talk about a few specific instruments. So first is just the LRO camera. It's a visible wavelength camera. We have the Lyman Alpha Mapping Project, which is a UV camera, and then we have the Diviner instrument, which is a thermal infrared camera. Okay, so this video here, which I'm glad it's playing, shows how essentially LRO makes maps of the moon. So it's in a polar orbit, which means it goes up and over the pole each time it orbits the moon, and the moon is basically rotating underneath it. So it's seeing a new area on the surface basically every time around, and you're over the course of months or years, you're basically building up these complete maps of the entire surface of the moon. And you'll see here, this is 27 days worth of orbits. It's 348. We've been orbiting the moon for almost 17 years, so this is like tens of thousands of orbits that we've been collecting data for. Okay, so this is kind of just to show how the different instruments with LRO work. So the LROC is at visible wavelengths. LAMP is the ultraviolet instrument, and then Diviner is going to be that thermal infrared instrument. So each of these instruments sees basically slightly different wavelengths of light. And okay, so first, here are some images from LROC. So LROC, like I said, is a visible camera. So it collects these really, really high resolution visible wavelength images of the moon. Sorry. But it doesn't just sort of collect these images to make these nice mosaics. It actually collects lots of really cool images, such as this one sort of looking off the horizon of the moon. This is Earthrise, as seen by LROC, sort of looking over all these mountains and craters. We have these nice, really detailed images of fresh impact craters. This is, meteors hitting the surface and ejecting all these different types of material from beneath the surface. The moon was volcanically active previously, so it has all these sort of ancient remnants of volcanism, like these volcanic domes surrounded by a whole bunch of volcanic floodplains as well. And then this is a crater central peak. So this is basically when a big enough crater forms, it actually sort of rebounds and creates these big mountains in the centers of these craters. And if we zoom in, we can see some really, really awesome details. So, some of these boulders are like tens or hundreds of meters across. And so we see lots of really, really cool details with LROC. We can also see actually landing sites. So this is the Apollo 15 landing site. We have all of the other Apollo landing sites, as well as these upcoming and sort of more recent in the past 15 years or so landing sites that we can sort of see some of the changes that were brought about by sort of rover or astronaut disturbances on the surface. Okay, so this video just shows how we're going to look more closely at the south pole of the moon. So I mentioned that we are really interested in the potential resources on the moon. So this includes basically water ice at the poles to use for if we ever have a base there, if we want to use the water for fuel. If we look at the poles of the moon, there are these really deep, dark craters which don't receive any direct sunlight over the course of a year. So they're really, really cold. They have the potential to sort of host this water ice. And kind of one of the main goals of LRO was to sort of identify the resource potential within these permanently shadowed craters. But the problem is, if you look at them in the visible, you can't really see much. So they're really, like I said, really deep, really dark. They don't receive any direct sunlight. So we can't really do much with it. But that's where an instrument like LAMP comes into play. So this is, again, a UV wavelength camera. And so LAMP is the Lyman Alpha Mapping Project. It's a far UV spectrometer, and kind of the really cool thing about LAMP is it essentially sees in the dark. So we see these illumination sources here, these bright UV stars, as well as this sort of faint, diffuse interstellar glow, or glow from interstellar hydrogen. So it uses these as the illumination sources to look inside of those permanently shadowed regions, because we can't really use the reflected sunlight to actually see inside. So if we look again, we can't see much in the visible, but we can actually see pretty clearly in the UV. And we can create these nice maps at different UV wavelengths. And so we can use these different maps that we create with LAMP to, again, look for the water ice or the resource potential. So this is showing that at these longer wavelengths, water ice reflects really strongly, and at these shorter wavelengths, ice absorbs really strongly. So we can make maps in these different regions and sort of look for that water ice. So this is kind of showing how exactly we do that. So this is a map at some of these shorter wavelengths. I feel bad. I'm going to say this a lot, right? Where it absorbs really strongly, but at these longer wavelengths, it reflects really strongly. So again, we can sort of use these different maps that we make to look for water ice at the poles. But we can actually use LAMP to look at the rest of the moon as well. We're not just interested in sort of the resource potential of the poles. We see that the lunar surface actually looks pretty different in the UV than it does in the visible. So, we have the maria, which are these sort of basaltic volcanic floodplains, which are really dark in the visible, but they're really bright in the UV. Some of these craters are sort of different as well. They're sort of these really low reflectance ejecta, and the high reflectance kind of right on the crater. We have these other features as well, such as like lunar swirls, which are these sort of weird, young-looking photometric anomaly type things that actually stand out really, really well in the UV. And so this is a map of some of those longer UV wavelengths, like I mentioned before. And then this is at the sort of the slightly shorter wavelengths, and we can compare the two, flip back and forth, that we see sort of slight differences between them. But one of the best ways to actually do this is to just take the ratio of those two. We see a lot of really cool features start to stand out. We have the maria, which I mentioned before, these sort of different type of composition in the rocks at those regions show up as really low ratio. Then we have the crater ejecta, which is this fresh sort of material that's been ejected by impact craters, shows up as really high ratio. So yeah, basically the UV gives us a lot of information, not just about water ice content, but also, we can look at the rest of the moon and look at composition and maturity of the surface as well. Okay, now let's look at longer wavelengths. So this is the Diviner instrument. It's infrared. And so this is essentially an instrument that measures thermal emission. So it's light that's being emitted by the surface. So you can use this to measure temperatures. And this image here, or this video here, is just showing how the temperatures change over the course of a lunar day. So The moon has no atmosphere, so basically the temperatures depend really strongly on basically the sun. So the sun rises, it gets, it gets kind of really hot. It reaches a maximum around local noon and then cools off towards dusk and then gets really, really cold and stays really cold during the night. And so as you can see, we're basically collecting data all, during the day and the night, pretty much nonstop. And so we're measuring surface temperatures, and we can use those temperatures to kind of tell a lot of different things about the physical properties of the moon. You can see here that, again, it's pretty hot towards the equator, and it gets really, really cold at the poles. And if we zoom in, this is looking sort of top down at the South Pole. We again see these permanently shadowed craters, which are, again, no direct sunlight. They're really cold, and so they have the potential to sort of host water ice. We do see slight differences between summer and winter. So this is a summer map, this is a winter map. It's not quite as extreme as the Earth, so the moon only has like a 1 degree axial tilt, but we do see some slight differences in temperatures for different seasons on the moon. So yeah, we essentially can use those temperatures we have, or the temperatures that we measure with Diviner to estimate where different types of ice are stable at the surface. So again, these are all sort of different potential resources, CO2 and water ice that are, basically boil away at slightly different temperatures. So water ice may be stable in the entirety of this sort of permanently shadowed crater right here, whereas CO2, I actually don't see much purple on here, but CO2 requires really, really cold temperatures. So we have to, if we're interested in CO2 ice, then we have to go look in really, really cold places. So these maps help us to know where to look for certain types of resources. Okay, and then this is looking at sort of the whole moon. Again, this is a thermal inertia map. So this is basically measuring how well the surface is able to hold onto its heat over the course of a night. And so you see, we don't see much difference between like Maria versus Highlands, but we do see some features stand out. We have these fresh impact craters, so they're really high thermal inertia. So this is impact craters ejecting rocks, and these rocks are sort of surviving at the surface. They hold onto their heat really well. They're high thermal inertia, so they show up as these sort of hot spots in the Diviner maps. Whereas this is a sort of pyroclastic volcanic deposit, which is this really rock-poor, fine-grained volcanic material that it actually has really low thermal inertia. It gets really, really cold during the lunar night. So we can sort of see differences in the physical properties of the surface based on some maps like these. And so we can actually get at surface composition with Diviner as well. So this is a Christiansen feature map. That probably doesn't mean anything, but essentially different types of minerals can emit light at slightly different wavelengths. And we can sort of see where these emission features are. And we can use that to estimate the types of rocks at the surface. So the lunar maria are, again, these sort of really iron and magnesium rich volcanic materials which show up pretty clearly in the maps, whereas the lunar highlands, which is sort of really low iron and magnesium, they're pretty different compositionally from the maria, show up pretty clearly as well. So yeah, basically the infrared, we use it to measure surface temperatures or thermal emission, and then we can use those to get at ice stability, regular physical properties, how it heats and cools, as well as surface composition. So the infrared wavelengths can really tell us a lot of different things as well. Okay, and then here's my takeaways. Basically, if you take one thing away from this talk, it's basically, LRO has been operating for almost 17 years now, and it's really collected tons of awesome data, created tons of really cool maps across a wide range of wavelengths. And then these different wavelengths, that's the last one I sort of can tell us a lot of different things about the lunar surface. And yeah, thanks.
We got two. All right, thank you for, literally. This one's a little. Reminder, the number's on the screen if you'd like to text in a question. We'll start with, what is the benefit of doing that polar orbit versus a traditional equatorial orbit?
Yeah, that's a good question. So basically, I think I...
Uh-oh. There you go.
Yeah, I don't have to go. But yeah, basically the benefit is that you get to go up and over the moon, and while the moon rotates underneath you, is that you get to see a new area of the surface each orbit. So if you're in an orbit sort of around the equator, you're basically seeing the same region every time you go, unless you sort of turn to look at a different location. So you get to really build up these maps using the polar orbit.
Very cool. Thank you. Does LRO give information about potential resource purity? That is, for example, if ice has dust in it?
Yeah, that's actually a really good question as well. You can try and use sort of some different instruments to get at that. I mean, I think the assumption is that any ice we see is going to be pretty dirty on the moon, because we can estimate, how likely the surface is to have sort of been bombarded by meteorites over time. And we say that you're more likely to sort of mix up this ice with sort of this dirty, dusty material on a faster timescale than you're likely to sort of get a fresh layer of ice on the surface.
Very cool. Thank you. Is there any potential for liquid water anywhere on the moon, or is that not possible?
I think that's not possible. There's the lack of an atmosphere, and that's really the limiting factor. And then you get really, really high temperatures during the lunar day, so it sort of boils everything off, turns into gas. And then if you get really, the only places where ice or water can survive is in the really, really cold temperatures where it kind of immediately freezes. Right. So liquid water is hard.
What would you say was the most shocking finding of all your time with LRO between both instruments and whatnot?
Yeah, I don't know. That's a good question. I don't know. Maybe can I try and go back to different?
The other direction.
Oh, this way?
Yeah.
Oh, okay. Oh, yeah. Good point. I may look at like a map, kind of like these maps here with LAMP, which kind of shows how clearly a lot of these like maturity-related features stand out. When I first started working on LAMP, I was kind of more interested in the poles and like the resources and stuff. And I started looking at some of these maps, and you see a lot of these like sort of fresh impact craters and features start to stand out, which tells us that the UV wavelengths can tell us a lot, about sort of how long this material's been on the surface, rather than just sort of getting at that ice question.
Right. How does wavelength help determine composition on the moon? Do you compare to known areas on Earth that are high in iron, carbon dioxide, for example?
Yeah, pretty much. So a lot of it is with lab experiments. So you can say you take a rock on the surface, you can measure it, it's this percentage iron, this percentage magnesium, whatever else is in a rock. And you can see sort of the different spectral features, the different features with respect to wavelength. And then you can sort of take the same data using the orbital spacecraft and sort of compare that to the lab experiments that we have on Earth, and sort of say, okay, we can estimate that this is a certain percentage of iron or magnesium based on what we know from the lab measurements.
Right. Interesting. Has anyone done change detection on the visual images?
Yes, actually, yeah. There's been a lot of work on that. There's, even over the course of like the past 17 years, there's been a ton of fresh impact craters. Now, most of them are pretty small. So LROC, which is a visible wavelength camera, has the really, really high resolution, less than a meter resolution on the surface. So you can see these fresh impact craters and sort of the fresh splotches that they make. So yeah, there has been a lot of work on that. And actually, I think we want to try and do some analyses with LAMP as well.
Very interesting. Let's see. Is there any way to use any of these tools to figure out anything under the surface, or?
Actually, yeah. So I would say the infrared can sort of tell you a little bit about the near subsurface, but I also showed that there was, or I didn't talk about it, but there's an instrument on LRO that's a radar instrument. And actually, it's an active radar, so it shoots out a radar wave and then measures what comes back. And so the radar wave penetrates a meter or so into the surface, so you can tell a lot about the subsurface with an instrument like that.
Very cool. All right, I always like to try to end off on a fun one. So, can we make beer on the moon?
Can we make beer? I don't know how to make beer, so I don't know.
Well, can we, the fermentation process?
The
do you think that can
process. That I don't know, although, hey, we're going to put a base at the South Pole of the moon. I assume they're going to be drinking some beer there. So.
There you go. All right, let's thank our speaker once again. Thanks, Ben. All right. And I want to thank you, audience, because there was a lot of questions this time around. So that's always fun. It makes my job easier. Pardon me. There we go. All right. I don't know why we insist on putting 5 to 10. It's a 10-minute break. It's going to be a 10-minute break. So we'll come back at 42 with our next speaker, or I'm sorry, with our AOT in the news with Jasmine. But for now, gaze upon Ethan's beautiful image. And like I said, if you have a very beautiful image of your own, please send it to samuelharthelio@gmail.com. Also send any complaints to that email as well. In the moon topic, feel free on our merch table up front here on the rightmost table. We have some lithographs of lunar informational stuff and pretty pictures. Those are free. You can take as many of those as you'd like. They're meant for outreach, and that's exactly what this is. So please feel free to take from the right side of the table. Thank you. All right, everyone, while Aaron gets us back going again with the PowerPoint, we'll settle back in, please. And I do want to note that a reminder that we have the final 2 shirts here, and they're small size. And I'm mentioning them, I'm bringing them up because, so these were and are $15. That beautiful new logo that's on the first slide, the colorful one, that helmet, oh, it's in the corner? Oh yes, this beautiful logo right here, will be coming on a shirt very soon, within the month, ideally. We'll see about that. But we do know for a fact that those shirts will be $20. Literally inflation. But the good news is that with that, we will also be able to do, so it's a snowball effect. So you get the shirts, and then you can also get stickers and more beer glasses and maybe even some pins. So support our local AOT economy with these shirts that we're going to get. So hopefully in March we'll have them, but for sure we're in the process of ordering them, and we're very excited to get them out to you. And we'll have a plethora of sizes. So just like we did with these shirts way back when. So we're excited about that. All right. Our next part of the program tonight is Jasmine Singh, who is our full-on astronomy in the news person with the departure, yes. With the departure of Dr. Caleb Gemar, she has big shoes to fill, but you know what? I remember from her talk, but I remember from her talk, right? Her job is not to be Caleb Gemar. Her job is to be Jasmine Singh, the one and only. So, yes, so here we go.
Okay. Well, hello, everyone. Happy 2026. I'm a little nervous. There's a lot of people here, so bear with me. I'm also not Caleb. First time doing it completely solo, so again, bear with me. But yeah, today I'm going to be talking about a plethora of things, mainly Artemis 2 that you can see in the picture. I thought this was a really cool picture, so yeah, let's just get into it. Oops. Okay. So my graphic is not as good as Caleb's. Again, bear with me. It's going to take me some time to get, situated with how to do this. But for February, Orion, which is my personal favorite, is going to be front and center in the late evening around 10 p.m. So you can follow the 3-star belt, and if you follow that down, you can find Sirius, which is the brightest night star in the night sky. In terms of planets, Jupiter is going to be the main planet that's visible late at night. That one's pretty easy to spot because it's very, very bright, and it's going to be up for most of the night. In terms of Mercury, Venus, and Saturn, those are going to be mainly visible in the early evening and twilight. So catch them right after sunset. But you're mostly going to be looking at Jupiter in terms of planets. In terms of best deep sky viewing, that's going to be around the new moon, which is around February 17th, the day after my birthday. So yeah, so if you want to have some really good skies, go drive out somewhere around that time and it'll be good. And in terms of good objects to view, with your binoculars or something, we have the Orion Nebula, Beehive Cluster, and the Pleiades. Those are always fun to look at this time of year. And then with your telescope, there's a cluster trio that is really good to look at in February. So yes, I'm not very good at pointing, I'm sorry, but bear with me again. All right. Artemis 2, you've probably seen it in the news. Hopefully, the news hasn't been that great lately, but this hopefully is on your mind. It just got pushed back to March, actually. It was supposed to launch 2 days from now. But during the pre-launch test dress rehearsal, there was a liquid hydrogen leak, so they had to push it back to next month. But I'm really excited, because many of us in this room were not alive during Apollo, so we didn't get to see any of that. We didn't get to see humans land on the moon, so it's fun to see humans go back. Artemis 2 is not going to be landing specifically, but we're preparing for landing, so it's still exciting to see humans go back really far. The furthest humans have gone since Apollo, so I'm excited. So I guess be on the lookout for that. Okay. Really good news for a lot of us in this room. Congress recently rejected the big budget cuts for NASA. No. Yeah, they passed the 2026 funding, which largely rejects the administration's proposed deep cuts to science agencies, including NASA. NASA specifically gets about $24 billion, which is a small cut from last year, but far less damaging than what was going to come of it. So still a victory, very much so. And missions and grants are not going to be as disrupted as we feared before. So a lot of us can keep our jobs, Yeah, I have hope that I can get a job in the future now. All right, this you may have seen in the news. I didn't hear about this until recently, actually. I don't know, very bad of me. But there was actually a rare medical evacuation on the ISS last month. I don't know how many have heard about that, but I wanted to talk about it because it's really interesting. So in about early January, there was a medical situation. We don't know the specifics, but it led to a rare early return from the ISS, ending the Crew 11 mission sooner than planned. Again, we don't know the details. They kind of have to keep that under wraps. But it's funny because it sounds like the plot of a movie. I can't say anything. But it's interesting because it kind of, highlights the reality that space medicine, this emerging field, kind of has to be prepared for these kind of emergencies, even when we're already in orbit. And it also helps us think about future long-term missions like to the moon and Mars, where getting home quickly is not going to be possible. So if we have an emergency out there, it won't be as good. So, but everyone's okay. I hope that's clear. Everyone's good. So, yeah, it was the first of its kind. Okay. Last but not least, I had to talk about Europa. I'm kind of biased. Yeah. So there was some recent reanalysis of Galileo data that shows signs of ammonia-bearing compounds on Europa's surface. And, this ammonia signal, it shows up near these kind of cracks, which matters because the cracks, in terms of Europa, they allow that material to transfer between the surface and the ocean. And so why does this even matter? Well, ammonia contains nitrogen, which is important for life, and that could change how we think about Europa's chemistry. Now, that doesn't confirm anything, but it's still really exciting in our quest to understand the icy moons and explore them. So, when Europa Clipper gets there in a few years, hopefully we can add much more information to this. Last but not least, new images. I'm always going to put the new images. This is part of the Helix Nebula. It's like the bottom portion of the Helix Nebula, the one that looks like an eyeball, taken by James Webb. This is a beautiful star-forming region from Hubble, and this is, I don't know how to say it, I think it's Cepheus, okay, from Hubble. So, yeah, go take a look at those. There's always new images coming out. I love to see it. You love to see it. Okay, there's a ton of events happening. I wanted to point your attention to the first Friday stargazing, which will be this Friday at the Flan Science Building at UTSA, the 4th floor, actually. And then there's also going to be a lecture. Well, that's going to start at sunset. But then there's also going to be a lecture at 7:30 about the auroras in Texas. So if you're interested, check that out. For the foreseeable future, there will not be South Llano stargazing because I think the park is closed for a little bit, so sorry about that. But it'll pick up as soon as they open and that's available. In terms of SAAA, there's the Messier Marathon from March 19th to 23rd at Fort McCavitt. So you can email here for more info. Every Wednesday, they do observing at Raymond Rinkus. First Fridays at Scobie. There's a monthly meeting on the 13th at 7:30. And then the 21st and 28th, separate observing ventures at Crescent Bend Nature Park and Guadalupe River State Park. And then if you want to go to Scobie, they have events every Friday at 6:30. Thank you.
Thank you, Jasmine. Next up, we're going to have Dr. Chris Bert. As a recent graduate of the University of Michigan and now a researcher at SWIRI, Southwest Research Institute, I get to help explore the solar system. That's Chris. Wearing my scientist hat, I study the sun, the plasma environment it creates, and its interactions with the planets. Wearing my engineer hat, I design instruments and develop missions to go out into space and make the measurements that then lead to more science. And Dr. Chris Bert, what is your drinking word today? Orbit.
Okay, thank you all for having me. This talk, I'm going to talk about Mercury, maybe a less often visited place in our solar system. I thought the title was fun, and it is very hot and cold because it is tidally locked to the sun in its orbit. But more generally, I want to sort of talk on, I think we're all in this room in agreement that space exploration is cool, we should do more of it, but we might find it hard to pick, right? And in the case of limited resources, you do need to make these science cases for why a particular thing is interesting and how you're going to accomplish that science. So that's also what I'm hoping to talk to you guys a little bit about. Make sure we're all on the same page. Mercury is that first planet next to the enormous sun there on the right. But then when you look at all the planets lined up like this, you might start to ask, like, why would we go one place versus another? First, I don't think I have a pointer on this. First of all, first of all, we're all very interested in the one right here because that's where we live. But then as we're going outwards, then what might you look for? Well, they're grouped in big categories. So these ones are giant and filled with gas. These ones are in closer orbits. And they're all rocky. So that's sort of one way you could separate it. You're studying different things such as why are these gases different abundances than what you find in the sun? Does that depend on distance? How have they changed over time? Then if you're looking for things that are more like Earth, you look at these rocky ones. Some of them have atmospheres. Some of them don't. Some of them have magnetic fields. Some of them don't. You might begin to ask why that is. A lot of people begin to ask why that is. And when the scientific community comes together and decides on sort of what are the big open questions and how will we answer them, things like why are there rocky ones versus gaseous ones and why do only some of them have magnetic fields come up as open questions that we have to then build these missions to go answer. So Mercury in particular is interesting because, like the Earth, it has a magnetic field. It is a rocky planet. Its orbit is on this inner part of the solar system. Unlike us, it is tidally locked, which is where the fire and ice comes from. So every 2 times it goes around the sun, it only rotates on its own axis 3 times. So that means part is facing the sun and baking for a long period of time. And at the same time, the thing that's in shadow, because there is no atmosphere to move that heat around, is freezing cold. And as with the moon, you have these craters, if they're deep enough at the poles, to trap that water, and it stays permanently frozen, along with the things that get trapped in that ice. So we decided that it was an important thing to at least fly by, and that was the Mariner 10 spacecraft launched in 1973. Now, it is harder than you'd think to go inside, in towards the sun, because even though those orbits are smaller, that actually means that you have to slow down, and that's tougher than you'd think. So Mariner settled for flying by a few times, and they saw all sorts of interesting things. which was enough for the scientific community to then say, okay, we're ready to build a big enough rocket and do even that much more engineering to put something into orbit around Mercury. And that was the Messenger mission, launched in 2004, and it took all the way until 2011 to get there. It did some flybys in between, and that was actually to give some of its momentum to those planets to get it to slow down. Finally, it was captured in 2011, and it had enough fuel to keep itself in a stable orbit until 2015. And then they actually ended the mission intentionally crashing Messenger into the planet, so that during those last few minutes and hours, they could get lower and lower and lower altitude data before splat. So it is still there, alas, just not transmitting. And then now we have Bepi Colombo on its way to Mercury. Fingers crossed, showing up in November 2026. And I say fingers crossed, one, because you should always cross your fingers, space is hard, but two, because we're using a novel, relatively novel form of propulsion called electric propulsion, which means we can, instead of having one big, quick thruster burn, you can do a little bit of momentum change over a long period of time, and that introduces all sorts of new calculations to how you're doing these trajectories, and that is a work in progress. So it may be, depending on the engine's performance, we show up sort of another couple go-arounds later, which may put us into 2027. That, and as we'll talk about, Bepi Colombo is a European and Japanese collaboration on which we do have an American instrument. So, Mercury, that close to the sun, as I said, like the Earth, it has a magnetic field. That magnetic field stands off some of the solar wind, so the sun inflates this enormous bubble of hot, fast gas around it that runs into this magnetic field and flows around it like a rock in a stream. It then has an iron core, like we do. And then we sort of, those are the big ticket items, especially as a heliophysicist, are things that I think about. But studying the planets is how we verify interesting details about general relativity. If we have a spacecraft putting out radio signals orbiting the planet, we can then have a much more precise measurement of actually how fast is it going around the sun. Where is it right now? Is it wobbling? And some of those wobbles, relative to what you might think is the regular oval-ish orbit, are instead what general relativity, in fact, predicts should be the case. Also, like the moon, Mercury is a place where there is no air, and so the craters don't weather away. You can see a full history if you take lots of detailed pictures to the extent that it hasn't been wiped out by new craters. You can see the history of the surface written for us to look at now. I'm sure I will go forever if I keep talking. There's these, ESA made some nice promotional slides, and there's lots of stuff that we can look at. There's a reason why we keep sending things to these planets. Stepping for a moment into the helio, when we're, this is called a chronomass ejection. The sun is occasionally coughing out chunks of its atmosphere into the solar system, and when that rams into these planets like a rock in a stream, sometimes that push can be hard enough to cause significant effects on the surface, and that is even much more that's even much more the case at Mercury. But even at Earth, 2 years ago at this point, the sun was having enough of an effect that basically John Deere had to tell farmers not to harvest your fields for a couple days, or otherwise the automatic harvest paths of your GPS-driven tractors are going to be far enough off to mess up what is a couple months of continuous driving. This is why that's a economically important but relatively minor in the grand scope of what could happen example of why there's the discovery science that we love to do for agencies like NASA. And then there's the other side of it, where the same people study what's the worst that could happen, and how do we monitor that, and how do we prepare for it? So like the same people who study ocean currents also study how do we know when the tidal wave's coming. And that's the equivalent here, right? You need heliophysicists and planetary scientists saying, we want to understand how all of this works, and we also want to understand when the big one's going to arrive. And, you know, throw the lever on the power grid for half an hour so that it doesn't poof. This I just thought was really cool. Another illustration that Mercury is close to the sun. This is from Solar Orbiter, one of its imagers, taking a picture sort of across the solar atmosphere with Mercury in the background. And sort of, yep. There we go. You know, and you can see this is, everything is moving very fast in a very big space. So that is very, very far away, but let's not forget that it is an entire planet, and that therefore these things are, you know, sort of screaming along in their orbits. This is a much more detailed version of what that solar wind and Mercury interaction looks like, and maybe we'll come back to this as we talk about what Bepi Colombo is trying to do as it flies through. But you begin to see with the different regions shown here by color why you have to pick the orbits that you do for different science goals. I'm interested in looking at that region, and I want to know what this boundary crossing looks like, and I want to be able to revisit this area that hasn't yet been affected by Mercury. There's a lot of planning that goes in. There's a lot of questions that you have to ask as you're thinking 10, 20 years down the line. What is this scientific observatory going to see? So, as I said, Bepi Colombo is making closest approaches as it desperately tries to slow down to get slow enough to be captured into orbit around Mercury. This latest one was only 295 kilometers from the surface of the planet. But it goes by at something like 5 kilometers per second. And then you can see there's an enormous list of instruments here. We'll talk. Serena is the suite. So not all of these are single instruments. Some of these are suites of instruments are involved in this kind of mission. And now, if it plays, yes. You can imagine it's very far away. You have limited bandwidth on your radio, and you want to take very high resolution images. And so you can take, you know, our radios are pretty good now. You can take very detailed ones, but between moving quickly and high resolution, you tile them together like this. It's a movie, but it's only a few images before you're gone again. That's why we can't wait until we're in orbit, which, as Ben showed, you can keep taking more and more and more pictures. But yeah, you can see big craters. The sunlit side is bright and reflective. The dark side is, it's dark. There is no sunlight on the other side. There's nothing reflecting back onto that night side. So you are kind of, you either have to wait until it comes into sunlight, or, as was shown earlier, you pick instruments of different wavelengths, and you, almost got you. And you look at it even at night. You can see the surface of the planet. You can, let's see. Yeah, and then, you know, you have, so here, we are at what the last slide was, but I wanted to add that 295 kilometers is basically the distance to Houston, and at 5 kilometers per second, you'd get there in about a minute. So just trying to illustrate the scale that we're passing by at. I know Houston is not close, but when the thing you're coming close to is the size of a planet, you know, some significant fraction of the size of the Earth, that's really close. I think I maybe have mentioned several of these already, but just to illustrate again, the sheer variety of science that you can do the sheer number of questions that visiting another planet can help you answer. And the reason why you need the great number of instruments that are packed onto what is ultimately not a huge spacecraft, especially because, as I said, you only have so much rocket power. That means you have to cram everything you can into as little mass as humanly possible. So we talked about, the magnetosphere. That's what we call the environment set up by that bar magnet-like situation you have with the Earth and Mercury and other planets like it. An exosphere. So we have an atmosphere. It's governed by all the little particles of air running into each other and scattering and acting like a gas, whereas an exosphere is these particles, there's not enough of them to collide with each other. They're gravitationally bound to the planet, and so I tend to think of an exosphere as each particle can make at least one orbit around the planet before it runs into another particle. Think that it's more orbiting than it is a gas. You're talking about, origins of various things that you find in the exosphere or on the surface. So one, as I said about the gas giants, why does it have those elements in it? Why did it form this way? Is that dependent on radius? But also, have they migrated around the surface? Or have they been kicked up so that sun-facing side gets baked and it is throwing off not just gas, but there is gaseous sodium, so metals, but individual particles that got hot enough that they stay up there and got kicked off by impact collisions and other processes. Unique surface features. We talked about cratered surfaces like this preserve the history of the body and allow you to sort of look back in time and understand what's happening in the solar system as a result. Shadowed craters, just like the moon. You're looking at stuff that gets trapped because it is cold there despite fire on one side and ice on the other. It is just cold all the time in some of those deep pockets. Crazy things like, is this planet shrinking? Well, apparently so. And that's due to all sorts of interesting things about how rocks work at that scale. And again, why is it made the way it is? Volcanism, we see that in many places around the solar system, but it's different in many places around the solar system. And why it's different is its own can of worms that I'm not an expert in, but is still cool. And, it's offset magnetic field. I said a bar magnet. You kind of would naturally assume that the center of the bar magnet is the center of the planet, but it's not. And we actually don't really know why. It's a big question mark. And finally, I said there is a U.S. contribution. On one of the two spacecraft, there is the Mercury Magnetospheric Orbiter and the Mercury Planetary Orbiter. We are on that second one, which is closer in, part of the Serena suite. And this instrument is called Strophio. It is a neutral mass spectrometer, so we are looking at gases in that exosphere that aren't already charged, so aren't already positively or negatively charged. And that forms a critical link between the two, and the fact that you have multiple points of observation with different instruments sort of opens another whole world of possibilities that you can do for science. And have SWIRI will travel. We have a Southwest instrument. We have Southwest instruments all over the solar system, and this is yet another example of us sending those very far afield to do novel things. And with that, I'll open for questions.
Thank you so much. Great. Oh, all right. Well, okay. Great talk. Thank you very much. And thank you for going easy on us. There were a lot less orbits and wavelengths. I had to throw that one in there for you. All right, here's a good one. Why is it called Bepi Colombo?
Those are from the names of scientists that were key in these astronomical and planetary discoveries. We like to name craters and bodies and then missions after people who have been key in forging those scientific paths.
Very good, thank you. How much of the fuel weight of this seems like a complicated, okay. of the spacecraft upon launch is fuel used to decelerate the spacecraft to enter the Mercury orbit? So I guess how much of the total, roughly what percentage is used just for the burning to stop it? Slow it down.
I will cop out and say I don't know what the percentage of wet mass versus dry mass it was pre-launch. That is different with these electric propulsions versus chemical propulsions. But I will say something really cool about Messenger is that they managed to save fuel by effectively sailing on light with their solar panels. Light does impart momentum when it is absorbed in a surface. It's a little bit, and it doesn't matter here on the surface, but if you put a spacecraft out into space, one of the forces you have to contend with is that sunlight is pushing you around. And so when you get closer, the sunlight is more intense, and therefore, across that surface area of solar panel, they were able to get a non-negligible amount of momentum over the course of years of flying, and so they could slow themselves down just on the power of light.
Very interesting. That's, bless you. That's very interesting, the solar.
Yeah.
That's cool.
Well, and when you design even constellations in orbit around Earth, you do have to account for that, because it will throw your pointing off, for example.
Oh, wow. Regarding the process of getting instruments on such missions,
Yes.
what is the overview of this process, and how competitive is it actually to get an instrument on such a spacecraft?
So, let me start at the end. The selection is very competitive, right? There are a lot of teams that put in proposals for these funding opportunities. But those teams form relatively organically out of the community far before NASA or another agency ever officially says that opportunity is coming. It helps when there's a regular cadence of these chances, and so you can anticipate. But you need a lot of people with a lot of different expertises, and a lot of institutions with the capability of building these things to plan well in advance, work together, come up with identify the questions you want to answer, figure out how to answer those questions, figure out what we're capable of doing, and then tailor what you are trying to do closely enough that you think you can do it within the amount of money you have, within the amount of, I talked about mass that you have, all of these different resources that you have to crush your design into in order to make it able to fly and then selectable as the best proposal.
Right. Very cool. Very interesting. Thank you. What is the margin of error between slamming into Mercury or then passing by at 5 kilometers?
Ooh. Again, I'm not sure I have a number for you, but where this becomes interesting is it depends on when you do it. So if you make a small adjustment and you're already at the planet, it's not going to do a lot, right? It's force equals mass times acceleration. If you don't put a lot of acceleration in the context of a lot of mass, you're not going to do a lot. If you put that same tiny amount of acceleration in 10 years ago, the effect propagates over time, and you could miss that part of the solar system entirely. Right. So I know it's not a satisfying answer, but it depends. And that's the entire context for using this new kind of propulsion, because you can make those tiny changes over a much longer period of time, and it builds up.
Right. This one has to do with, this one's orbits. How is the process for settling down on the orbit path that you use for the mission? Is there a lot of jockeying? Is there a lot of infighting, or what?
Oh, do you mean picking which orbit to go to, or do you mean trying to maintain it?
I guess which orbit to go to. Once you're there,
okay.
Once you're there.
So I'd say that largely, that's a combination of which science we think is the most exciting to go after, and also the art of the possible. So you can only carry so much fuel. You need to maintain it even once you get there, but getting there is its own problem. But then, we were talking about I'm interested in all those different regions of the magnetosphere and how the solar wind is interacting. If I had my way, because I'm a plasma scientist, I would want the spacecraft to spin. You know who hates spinning spacecraft? People with cameras. And so there's this constant competition of what do we have it do, because the choice to stare straight at the planet is the less good choice for the people who want all sorts of funky ion and electron measurements, and you balance it.
Wait, hold on. I want to bounce off of that with a good question. That is, what is the main science goal for Strophio specifically?
Yes.
Is it about the atmosphere neutral composition, or the processes of what's like loss, or what is the main goal?
So one of the earliest sort of signs that there was something funky going on at Mercury was spectral observations of those metals, but in gaseous form in the exosphere. And so that exospheric composition is really one of the key questions that Strophio is going after. And if maybe you can imagine, neutral particles are a little bit harder to observe than charged particles, because you can't, with no charge, you can't bend the neutral particles anywhere. So it takes a few extra steps in the instrument design process to make them observable, which is part of the reason why it's been less observed. So it's going after that composition, but then that composition in concert with other instruments tells you all sorts of other interesting things too.
Very cool, thank you. All right, one last main question here, which I think is a very good one. What is the fuel of electric propulsion?
Forgive me that I forget exactly which one Bepi is using, but it can be a number of things. Electric propulsion is primarily governed off of, well, it's, okay, in that way it's the same as chemical propulsion. The rocket equation is basically how fast can you throw mass out the other end. And so you choose different fuels based on how easy is it to ionize, how easy is it to accelerate, how easy is it to store for decades stably? Will it come out of, in microgravity, will it come out of its tank, or will it slosh around endlessly and never make it through the hole? Not being my area of expertise, I don't remember what it is, but there's a variety of them out there, including water. Water is an example.
Cool. All right, and then our fun question. Which hat do you play your saxophone with? The engineer hat? Or the
Oh, I mean, the answer is probably both, right? I have a set of screwdrivers that live in my case because I need to fix it occasionally myself. But as a scientist, I was the nerd among band nerds, because I'm like, this is how sound works, and that's how long it takes this sound wave to get across the football field, and that's why we can't use that metronome, because you're hearing it like so, right? In a Sousa march, an eighth note goes by between the sound being created over there and the sound getting to the other side of the field, so the drum major can't be listening to anybody. It goes on and on and on. So yeah, I both from a science and an engineering perspective, band can be as fascinating as planetary science sometimes in my mind.
That may have been the most thorough, fun question answer I've ever heard. So congrats on that. Thanks to
Thank
Chris
you.
once again. All right, and, huh? What was the name of it? Xenon. Xenon is the fuel that they're using, apparently. So you know those headlights that annoy you that are not like the pre-LED annoying headlights? Those are xenon. Very blue. All right. Thank you again, audience, because I mean I had so many questions that I wasn't able to ask the speakers tonight. That's rare, actually. Usually I'm begging you all for questions. So if you didn't get a chance to have your question answered, I'm sure our speakers are okay to hang around for a little bit. Don't bombard them too much, but feel free to go up and ask them. But that ends our main program for tonight, so thank you all for coming. Yes. Thanks to Blue Star for having us, and we'll see you all at the first Wednesday of March. But if you can stay for trivia, what is it, March 4th? Yes, March 4th. If you can stay for trivia, we're going to get rolling right into it. We'll come around with the answer sheets and a writing utensil, and give us about 5 minutes. Today's theme is the St. Valentine's edition, so there's love in the air. All right, folks, let's get going. Let's get trivia-ing.
Everyone has a sheet.
We're tangled up.
Everyone has a sheet. Everyone has a utensil. All right. Speak now, forever hold your peace.
A reminder, max group size of 4 per team. If you have more than that, split up and we'll get you another sheet. No cell phones. We are honorable in this room. And please write only the letter choice for the multiple choice answers. Yeah. Is everybody ready? All right. Question 1.
Odds. Number 1, not binary. The famous double star system Albireo is located in which stellar constellation? Is it A, Orion, B, Lyra, C, Cygnus, or D, Gemini? And do not fret. If we move on, we can come back.
All right. Question 2. Out for delivery. Which physicist wrote a love letter to his late wife with the words, "Please excuse my not mailing this, but I don't know your new address. And you dead are so much better than anyone else's alive." Oh, that's so sweet. That's really sweet. I mean, I get that sentiment. A, Albert Einstein, B, Edwin Hubble, C, Robert Oppenheimer, or D, Richard Feynman. All right, we'll move on to question 3.
What if we kissed on STS-47? Jan Davis and Mark Lee are the only married couple to fly to space together on which space shuttle? A, Endeavour, B, Columbia, C, Discovery, or D, Atlantis? They informed NASA of their marriage in 1992 after the flight roster couldn't be changed. Unfortunately, they divorced a few years later. It's just not the same on Earth.
Okay, we'll move on to question 4. This well-known physicist chose, voluntarily celibate, chose to remain celibate throughout his life, claiming, quote, "I do not think you can name many great inventions that have been made by married men." Interesting, end quote. Was it A, Isaac Newton, B, Nikola Tesla, C, Marie Curie, or D, Paul Dirac?
All right. Question 5. Hit that button. At long last, pictured here is the merger of two galaxies within the smaller galaxy NGC 5914 being Pictured here is the merger of two galaxies. Oh, okay. With the smaller galaxy NGC 5914 being consumed by the larger galaxy, known colloquially as what? A, sombrero, B, Andromeda, C, whirlpool, or D, cartwheel. Bonus, half point. What is the Messier number of the merging galaxy? Write that next to your letter if you know the number.
A reminder that the Messier Marathon is coming up. The 110? No. 110 Messier objects.
Hunting for comets.
Yeah,
The Messier catalogs all the things that are on comets.
that's true. All right, we're going to question 6. Let's get some sun. Taken by the Solar Dynamics Observatory on September 10th, 2025, very recently. This heartfelt photograph, which also kind of looks like a butterfly, of the ultraviolet sun displays what dark feature? Is it A, a sunspot, B, a butterfly diagram, because the sun is very smart, it can do that, C, a light bridge, or D, a coronal hole? Which one of these is seen in this image?
All right, does anybody need a question repeated? Hold up your fingers if you do. Going once. Going twice. All right. Everyone's good?
Bonus.
All right, this goes in the bonus section because that's where the bonus question goes. The bonus question, asteroid 26591 and 26592 are the only 2 asteroids to be named sequentially by a husband-wife duo. Asteroid 26592 is named Mary Renfro. What is the name of asteroid 26591?
Objects in the mirror are closer than they appear.
Last chance to repeat a question. Does everyone have their final bonus question in the bonus section?
When you're done, bring your sheets and writing utensil, if we gave you one, up to the front. Thank you very much. All right. We have the results, but first, let's go through the answers.
Numero uno. Where's Alberio? The Swan, Cygnus.
So I was confused about this one at first, and then Aaron was very astute, telling me to use a process of elimination, because Gemini, the twins, they don't have anything of note in them. They're just twins.
Not to my mind. I'm
Yeah.
sure there are some notes, but
Orion, as we all know, is Betelgeuse
and Rigel.
and Rigel. And then Lyra has Vega. So that leaves only one option that even if you didn't know what Alberio is. Alberio, sorry. Wait, that's a wine.
Albino.
That's a wine, and we have to talk about that. And so that was process of elimination.
Highly recommend seeing it in a telescope. It's very pretty. The gold and the blue is a very weird combination. Super weird. Is Alberio, does someone know in the room, is it a binary? Go blue, yes. We're going to get there, trust me. Someone has a sweatshirt on, go blue. Go blue. Is Alberio an actual binary, or is it a visual binary? Yeah, I thought so. So they're not actually orbiting each other. Woo. They just look like it. They're just next to each other in the sky. Fun fact.
What do they call those? Optical binaries?
Visual binary.
Or visual, yeah. All right, this next one threw me off because I wasn't expecting it, but it was a very young, the love letter was a very young Richard Feynman.
Oh, wow. Very, very young Richard
Yep.
Feynman.
So there you go. You dead are so much better than anyone else alive. That's a great line. I'm going to use that. Anybody.
It only comes in handy once.
That's the joke. Okay, all right. Question 3.
Question 3.
The Kissy Space Shuttle.
I freaking knew it. Next.
I'm sorry.
Endeavor. I don't know why I know. I know just my guess. Yeah.
All right. And this was STS-47, right? Yeah. So,
Yeah.
for those keeping score at home. All right, question 4. Who was the one to remain celibate throughout his life, claiming, "I do not think you can name many great inventions that have been made by married men"? And the giveaway for this one was inventions. There was only one real inventor on that list, and it was Mr. Nikola Tesla. And the he was hiding stuff in the mustache. That's the story. Well, I can't touch calculus, I can't.
Hey, no.
I can hold a Tesla coil. I can't touch a area under the curve. I don't know. Aaron.
Question 5 at long last. Name that galaxy. Whirlpool. M51. Get it? Because it's like a big whirlpool. The sombrero is a big disc. Yeah.
The sombrero is edge on.
Yeah.
You're viewing it. That's why it looks like a sombrero.
Andromeda is Andromeda.
And yeah,
It's
that's
big.
not merging. Andromeda. Who is Andromeda going to merge with? Thank you. Very good.
It's
Okay. Well.
stick around. Yeah, stick around 2 billion years. We'll find out.
And
Yeah, stay tuned.
and nobody cares about the cartwheel. We don't talk about the cartwheel.
Hey, the
Sorry.
car was nice.
All right, this next one, it threw some people off, and I'm glad because we're learning something new. That is not a sunspot. That is a coronal hole. Very good. Yes.
Why do we know that?
A
Why do we know
sunspot-
that?
A sunspot is visible. This is in the ultraviolet. There you go.
And it's also like freaking huge.
It's huge. A sunspot could never really be that big, I don't think.
If it was that big, we would have some problems.
Yeah. Exactly. There you go.
SamuelHartHelio@gmail.com. That's.
No, I thought this was a great question.
No, I agree.
Yeah.
You got us.
Like I
Well,
said,
not us.
if you didn't know it, now you learned it. We all learned something together. How sweet is that? All right. And the bonus, Aaron.
The bonus to the bonus, because that's where the bonus goes. Name that asteroid 26591. Robert Reeves. Our very own in the flesh right here. We all wanted to pay tribute. Robert consistently donates. Well, we've gotten, what, the whole stack now? Yeah, we got a year's worth of actual lunar prints from
Lunar Orbiter.
Lunar Orbiter. So. Yeah.
Right.
So actual prints. That's a teaser for you. Come back every month, first Wednesday of the month. Maybe you can win some prints.
Yep. The lunar prints will be our top prize every night or every event. So stick around. All right. Speaking of prizes, we've got some for you. All right. We'll start with honorable mention. We do this sometimes if we have like a close tie for third place and we want to give them something and we have something extra. So we have these cool LRO lamp stickers here, and we're giving it to older but not wiser. Honorable mention. Come on up. Each of you gets one of these beautiful stickers.
He got the bonus.
I hope so. All right, third place, which will get this cool Celestron beanie, those LRO lamp stickers, some LRO magnets, and a cute Bepi Colombo enamel pin.
Just one.
Just one.
Just one.
The winner is Star Masters. Come on up.
Do you want all four?
I guess, unless I'll take it.
Ethan, remind me why the park is closed again?
They're redoing the camping area.
Okay.
So maybe March.
Okay.
Ooh, I got a pin too. Thank you.
All right. Moving up to second place, which will get this cool poster of, was it X-ray? No, Fermi. Gamma ray, right? Gamma ray. Gamma ray. And then once again, sticker, magnet. The second place winner is Microphone Guys. Come on up. Hey. That better be put in one of your offices when I come by and look. All right. All right, and then our top prize tonight, which gets this beautiful projector. Thank you to Mark. And it better not be that. Wait, did you submit an answer sheet tonight? No, thank goodness. Because if you want,
Wait. Mark, are batteries included? I put the batteries in there. They're in. Batteries are included.
Amazing. Drum roll, please. Plutonic Love. What a name. That gets also the best name of the evening for our St. Valentine's themed evening. Plutonic Love is the grand prize winner.
Now, what's a pluton? I don't know. I know. That's probably.
Good job. Good job. Good
Oh,
job.
we have more stickers. Wait.
Good job.
No, Jasmine's there. Nick. Here, Nick needs a sticker.
All right. If you didn't get anything tonight, like I said, come back next time because I'll give you a sneak preview here. Here, take this off. Our first place prize at the next Astronomy on Tap will be each team member will get one of these. Look how beautiful that is. Ooh, ah. It doesn't get any more authentic than that. It does. Yeah. Aaron says it smells real. And shake it back in. Thank you. All right. That brings us to the end of tonight's program. We'll see you back here on March 4th. Thank you, Blue Star. Thank you, audience. Thank you, SWIRI. Thank you, UTSA. Have a good evening. And get home safe. Oh, yeah, do not sign up on the... We got to fix this. Oh, no.